All right, guys. So I hope you had a chance to review infinite series, at least a little bit. And what I covered, I think, will be enough for this course, right? So all the series that we consider converge. You need to understand what is e to the x. You need to understand the expansion. You need to know derivatives and whatnot. And I'll try to help if you forgotten something. So first chapter, we begin by discussing what is probability, right? We all calculate stuff, but what is that probability? And of course, guys, turn on the cameras, please, so that I may see my students, right? I enjoy looking at your faces. I see your reactions. I know if I hit the target or not. So let's begin by a simple question. So I will toss a coin. And what's the probability that this coin lands heads? So people say 1/2. Would anybody tell me what does this 1/2 communicate? So 1/2, what does it mean? Okay, so heads and tails, something like equally likely. Maybe some elaboration would be nice. So 50% landing heads, but so some of you are saying heads and tails equally likely, two faces, one of which is heads. So two faces, one of which are heads. So you might imagine that when a coin is tossed, there are two outcomes, heads or tails, right? Two universes. So you might say that the probability of heads is 1 out of 2. There is, of course, a problem with that, right? Today, you will either lose consciousness in the middle of the lecture or not. But those two possibilities, I'm assuming, are not equally likely, right? It's not just the two universes that can come in that sense are not, you either win a lottery today or not win a lottery, if you prefer that analogy, right? Those events are not happening as frequently. So there is something about frequency of occurrence that we must take into account. So here is the idea that should be somewhat intuitive here. What we can imagine is that this 1/2 should indicate somehow nature's preference to the universe where heads comes out as the result of my experiment. So how do I figure out what the universe prefers? So the idea is maybe I can throw the coin many, many times, ideally infinitely many times. And in the number of trials, nature will show its preference. Understand, guys, what's the idea, right? So when I throw a coin, there is some uncertainty. But the question is, maybe if there is a balance between heads or tails, that should be somehow resolved. So here is that experiment performed, okay? So I am going to throw a coin 20 times, okay? And I will record the ratio of the number of successes, that's when I received heads, and all together, all trials, so 20 trials, okay? So I will calculate this sequence, which is no longer deterministic. Yes? So first trial, you see, guys, here is I do run 1 and run 2. This is an actual simulation. I actually, when I did it, I threw actual coins, and once the numbers became very large, I just simulated on the computer. Okay. So here is actual coin. It was in trial 1. Look what happens. First, 1 out of 1. Then by second trial, I have 1 out of 2 because I had 1 success and 2 trials. Next, again, I had another trial, 1 out of 3. Another trial, you see, we had lots and lots of, look how many failures I had. This is actually very typical of randomness. Some people think that if you have too many outcomes in tail, then that's not a random sequence, and then you switch it. But randomness doesn't look like what people imagine. And when you try to fake it, it can be detected forensically. You see? So this can happen in randomness. And you see that in the sequence, by the end of 20 tails, I got about 8 out of 20 successes. Now when you see, so this is a sequence that I obtained here. NH over N is number of times in my experiments that H happened divided by total number of trials. And you can see that the sequence in round 2 is different from the sequence in round 1. The sequence is not deterministic. I do not know its terms before the experiment has been performed. And look at it. Here we had 8 out of 20 successes. Here we had 10 out of 20 successes. Here exactly after 20, I got 1/2 ratio. Here I had 8 over 20 ratio. Good. So then see what happens if I just here some 3 simulations or 5 simulations. In fact, when I toss the coin 10 times, 100 times, 1,000 times, and 10,000 times. Look what happens here. Look at the variation. So after 10 trials, the ratio got to be 0.5. Here the ratio is 0.6. Here it's 0.8, 0.7, and 0.6. There is some variability. Now, after 100 times, you can see there is still variability, but it goes down a little bit. And then in 1,000 throws of the coin, the variability goes down even more. And after 10,000 throws, you see the ratios are very similar to 1/2. You understand? So and you can see that actually even after 10,000 throws, you can still, most of you can detect the difference between 1/2 and this number of throws, right? Even after 10,000 trials, it's not really, it doesn't look exactly like 1/2 to you for those number of digits. Okay, so we make this informal definition of probability. So we will say that the probability of an event A is the limit of the number of successes divided by number of trials. You understand? It's the limit of that non-deterministic sequence. If the limit exists, then we have probability. You understand? So in other words, to verify what's the probability of the coin landing heads, I have to throw the coin infinitely many times and calculate the limit, right? I just throw it 20 times, calculate number of successes over 20. Throw it 21 times, calculate number of successes divided by 21 out of all the trials. And the limit of that sequence, if it converges to 1/2, that's what I mean by probability, okay? And the philosophy is that, nature will reveal its preference after multiple number of trials. Good. Now, it is rather hard to grasp the concept of probability. Well, one reason is that you don't experience performing experiments to infinity. And the other is that, at least if that's the definition, look at the problem. That even if I could throw the coin infinitely many times, there is no guarantee that if I reset this experiment and do it infinitely many times again, that the result will still be the same. You understand? Because the sequence is non-deterministic, and yet every time you perform the trial, it has to converge to the same value somehow. And how would you possibly, account for that? It's some sort of philosophy that we use here. Okay, so one way around it is that maybe somehow nature's preference before you begin performing this experiment, right? Somehow you can see that quality. So let me show you that example. Let's say, suppose that I claim that boxer A is twice as good as boxer B. So there are two boxers that are going to be matched, and boxer A is twice as good as boxer B. He has this quality imbued to him by the gods. My question is then, can you tell me what's the probability, and try to do it using this limit of a sequence? Can you tell me what, if that's true, must be the odds of, or the probability of A winning against B? You may assume that ties do not exist. So either boxer A wins or boxer B wins. You understand? Let's see if you can calculate it. Yes, no, good. But can you do that? I mean, it's still an easy question. I want to be sure that you do it by the limits, right? If you understand that limit idea. So obviously you don't need to type it. I will show it below, but just to be sure. Wonderful, guys. All right, 2 people already answered. See if the rest can follow. 2/3. Beautiful. Wonderful. You see that it's 2/3. Let me now show you how I carry the calculation. Okay. Here it is, guys. So A is the event boxer A wins. Now, if we run n matches, if we played n games, then the number of times boxer A won plus the number of times boxer B won equals to n. You agree? No matter what it is in any situation, we assumed that there are no ties. So probability that A wins is the limit as n goes to infinity of NA divided by n, which is limit as n goes to infinity of NA divided by NA plus NB. Now, if we believe that boxer A is twice as good as boxer B, then if n is very, very large, that means that that the number of matches that were won by A, it's 2 times the number of matches won by B. You see what I do here? So I say that NA is about 2 NB. And so here I can cross out NB and I get 2/3. Now, have you heard ABBA's song? I'm presuming you know that song, guys. The winner takes it all. Do you know it? There is a line in that song. You don't know it, so I figured we'll have to pause and play a song, which is what I always think about when I do probability. Good. So the line that we will try to interpret is, of course, this one. The gods may throw the dice, their minds are cold as ice, and someone way down here loses someone dear. All right, let's listen to it. Well, guys, you may turn your cameras back on. There is no shame if you're crying because of this emotional song. So let's get back to the calculations, guys. What do the guys do? You see, here we understood the nature of the die, right? It means that the gods do not care whether the number 1 or 2 or 3 or 4 or 5 or 6 come out. Using that information, using ABBA's information, calculate the probability of rolling a 1. Using the limit sequence, you understand what I mean? Obviously, you might guess 016, right? Somebody told you. Calculate it. Show me that you understand why that's the case. Well, Yufei. All right, guys. Ready? I mean, I know it's not convenient to write it in chat, so let's do it together. So here is the situation, guys. So we know that if we performed n throws of the die, then the outcomes 1, 2, 3, 4, and 5, 6, the number of outcomes of each situation add up to n, correct? So exactly, Alan, that's my point precisely. That's my point precisely. That's exactly what you think, or at least what I think of probability. So then what you have is n1 divided by that sum, but they are all the same. All of those are the same because the gods do not care what's the outcome. That means that 6 times n1. And so I can cross it out and I get my 1/6. Good? Now, this, I suppose, I mean, you think, well, so what? I kind of could predict a coin lands with probability 1/2 and that the die lands with probability 1/6 on the number 1. Now, let's see for the next question. What would you say? Suppose something has 0 likelihood of happening, 0 probability. You understand? So you ask a girl out and says, the probability I'll go out with you is 0. Does it mean she will not go out with you? So tell me, please. Right? If something has 0 chance of happening, does it mean it does not happen? Good. All right, guys, ready? So a lot of you said that that probability 0 means it never happens. Well, you are incorrect. Right? It's a sequence. If it's a limit of a sequence, it just means that that first of all, your days are numbered. So even if she marries you, the probability that she will go out with you is 0, because the number of times, the number of days she will be spending with you are finite compared to eternity of trials, right? And let me show you, let me actually tell you this, guys. So you see, you need to understand, probability 0 does not mean that something never happens. Okay, in fact, you experience, you know, you ask yourself, what is a miracle? A miracle, in my definition, is an event that has 0 chance of happening, right? And you experience those miracles every time you order delivery, right? Let's say you go and you order delivery from, let's say, Seamless or Uber Eats. And then you are told that your delivery is scheduled, let's say, between, well, let's say the delivery is scheduled between 12 and 1 o'clock. You know, it takes time to bring it. So you know that the delivery person, let's say, will come at any moment of time between 12 and 1 o'clock. And each moment of time is equally likely. Let's see what can happen, guys. What does it mean if each moment of time is equally likely? Let's see for a second. You see, guys? Moment is equally likely, so we can understand it like this. If you divide the hour into minutes, right, into 60 minutes, good, the actual moment of time of arrival would either be within the first minute or within the second minute or within the next minute, right? So there are 60 equally likely containers for the exact arrival of the delivery person. Agreed? Now, the probability that the delivery person will arrive on any particular minute is 1 over 60. Do you agree? But then you can divide time into further, smaller segments. And within each segment, the probability is the same. So in general, if I divide the time interval into n parts, right, the probability of arrival within one of those parts is exactly 1 over n, if I'm assuming that likelihood is the same for all moments of time. You understand? Which means the probability that the delivery will arrive at a moment t equal to t0, that's the exact moment, right? The exact moment when the delivery person comes, that probability is 0. Understand? So pick any moment of time, exact moment of time on the number line where the delivery person should arrive. The probability of arrival at that moment is 0 for any moment, but there will be actually a moment of arrival, right? One of those impossible moments will end up being the actual moment where you receive your delivery package. Do you understand? Now, naturally, we can ask the next simple question. If the probability of an event is 1, does that mean that the event always happens? And now you can see the answer is no, right? If you understand that probability, if you think of probability as a kind of limit, a limit can converge to 1 without always being 1. It just has to be 1 very frequently, right? And using that same idea, guys, the probability, fix any moment of time t0. The probability that the delivery does not come at t0 is 1. You see, so fix that moment of time, the probability the delivery does not come at that moment is 1. But you can actually run the delivery experiment several times and actually note a particular moment when the delivery person arrived. You see, the thing is, when you do repeated experiments, that moment is never repeated again. It's unique, right? So every time you receive delivery, you are experiencing a miracle, right? It's a unique moment that will never repeat, never has been before and never will be after. Amazing, right? Okay, so here is my hardest question. Think about it, guys. Could there be events that do not have a probability? Right? So the probability is neither 0 nor 1 nor anything in between. Okay, interesting. One person already says yes. Andre says no. Okay, guys. The answer mathematically is a bit clear, yes? You have seen sequences. Now, a sequence can converge, but it can also not converge. So an example of some event that does not have a probability is that if we create a running sequence for that event, the limit will not exist, right? The limit will not exist. Now, if you studied analysis, you are possibly familiar with the existence of non-measurable sets. There are sets that are non-measurable. Now, measure theory and probability theory are mathematically the same. See? They are just the measure theory is the mathematics of probability, and the existence of non-measurable sets is an indication of events that have no probability. But so that it would be very simple to understand, let me create a rather weird experiment, okay, to show you something that does not have a probability. Good. So imagine, guys, that this is the contraption that we have here, right? So when you turn on this contraption, to create a sort of simulation of probability, you have to create infinitely many outcomes. You understand? You have to create infinitely many trials. So let's suppose we have this machine where when I press the button on, like simulate, what the machine does, it randomly selects heads or tails, and then prints. You can imagine it prints infinitely many times heads, its state, or infinitely many times tails, its state. You understand? So when you turn on the machine, right, the machine will sometimes produce a sequence of only heads and sometimes produce a sequence of only tails. So you can see that the sequence does not converge because repeated experiments to estimate the probability fail. You follow what I'm saying? You might, of course, ask, what's the probability the machine will indicate heads? It will print out heads. This, of course, has probability 1/2, right? But if you ask what's the probability of heads, you're asking something else. You're asking, will this thing always be printing, a sequence of heads and tails where the ratio converges to a particular number? And you can see that sometimes the convergence of heads is to the number 1, sometimes it is to the number 0, so the limit does not exist, okay? And you might, of course, be annoyed by this example. I mean, you can take measure theory as another example, but that's too complicated, yes? But you might also argue that when I do the situation, right, when I record the next trial, right, that's my universe, I do not reset my universe. But that also happens when you perform actual experiments. You understand what I mean, right? So you might say when I press on, right, when I press on, and then print the outcomes, then the next time I repeat it, you see the machine enters the state. You see once I press on, the machine enters the state heads or tails, right? And to run the next simulation, I remembered this that it produced heads, and then when I run the next simulation, I turn the machine off, I turn it on again, and then I see the simulation. Okay. You see, guys, you have to perform the experiment under the same conditions, I suppose, right? So the question, of course, here is what do we call an experiment, right? To verify that the probability of something, according to this very difficult type of intuitive but very difficult definition, what do I have to do? I have to create an experiment in which I can perform infinitely many trials infinitely many times. And each time I perform this experiment, the results must be the same after performing infinitely many trials. Okay? So naturally, you cannot throw a coin forever. Okay? So here, I just imagine performing infinitely many trials, but when I start this machine, if it's in state H, I can presume that all the trials came out to be H. And if it's in the state T, I presume all the trials became T. Do you understand? So basically, when I repeat this experiment, the results are not the same, right? So my estimation of probability is not the same. Understood? No? Where am I losing you?
So is the reason that it doesn't have probability because it can be conducted infinitely?
No, so the reason I'm trying to suggest, it's somewhat of a weird example, but what I'm trying to suggest is this. If you actually try to verify experimentally whether something has probability, so for example, take a coin, right? How would you experimentally verify that the probability is 1/2? You would have to throw the coin infinitely many times and continuously calculate ratio of the number of successes divided by the number of trials, and observe that this ratio converges to 1/2, right? Now, if you perform this experiment, right? One experiment means throw the coin infinitely many times in my context now, right? So when you perform that experiment, even if you were successful in throwing the coin infinitely many times, can you conclude that the probability is 1/2? You understand what I'm asking? Suppose you did it once. So let's say today I wake up and I start throwing the coin, and somehow I was able to throw it infinitely many times. No, I mean, already preposterous. How am I going to do that, right? But suppose you were successful somehow. Is that evidence that the probability is 1/2 for the coin? No.
So my question is, Professor, like in the previous lecture, you talked about how for geometric series at least, if the ratio is between -1 and 1, it converges. So in that scenario, it doesn't have a R that's between that, or is it not a geometric series?
But where do you get geometric series here? It's just a sequence, right? A sequence converges. What does it mean for a sequence to converge? It means that if you print the terms of the sequence in a column and you look down the column, eventually starting from some very large row, maybe, it all looks like the same number. Okay, so if it's a numeric sequence, the numbers look the same. If it's some other sequence, the objects placed in that sequence begin to look the same. You cannot distinguish them, right? So for probability, the thing is we get a non-deterministic sequence. Before I perform the trial, I do not know what was the first outcome, second outcome, third outcome, and onwards, right? So as I begin, so intuitively, probability is performing that sequence, this running the ratio of successes divided by total number of trials to infinity, where the number of trials goes to infinity. Okay, And if I get a limit, then I know that then I hope I know that my sequence converges. You understand? Here again, to look at the initial table here. Do you see what happened here? Here is my run number one. It's basically running the experiment for first time. Imagine that this goes to infinity. This only went to 20, but it should go to 10,000 and then below to infinity, right? So here I run it once, and here is my sequence. Do you see? This is the sequence. Do you see the numbers? This is the denominator is the trial number, and the numerator is the total successes over all previous trials. You all see that? Now you see that if I run the sequence again, I get I generate an entirely different sequence. All right? So you understand that. How would I know that that this column converges? It's non-deterministic. I know it converges if I could look lower and lower and lower and somehow be convinced that all the entries begin to look the same. You see, so starting from maybe here it is, right? You can see here is the experiment performed 5 times, and this is looking at the 10,000th row. Do you see that they look alike? So I predict that in those rows they would all look alike. As you go lower and lower and lower, they will look more and more alike. You understand? The variability between them will be vanishing, and eventually maybe after trillionth trials you will see only 1/2. To you it would look like actual 1/2 through all the 5 trials. You see? But the problem is there are many problems. It's non-deterministic sequence, right? So if I could see all infinitely many columns, perhaps I can be convinced that they start looking like 1/2. But you understand that that even if I perform it infinitely many times, even then there is still a problem, because you see it has to converge every time you perform the experiment and generate an infinite sequence. This infinite sequence has to converge always, right? Mathematically very non-viable, right? That's not how you define probability mathematically, because well, how do you verify that, right? But intuitively that's exactly what you should think about, because that gives you the idea of what happens there. There is a philosophy here, and the philosophy is that somehow you feel that you understand nature enough, and you feel that nature has its preference, right? So outcome of probability 1/2 when there are 2 situations, that means nature does not prefer either outcome 1 or outcome 2. And that you might see because you think, well, there is nothing special about one side or another, so somehow you believe that there is no preference between heads or tails when you say it's 1/2 already, right? So when you say the probability is 1/2, you are kind of saying, well, I know what nature preference will be, and that will be shown in that limit. Good? So far good? So you understand the problem of actually verifying it. So even if you perform it infinitely many times, maybe the next time you perform it infinitely many times, the results are different, right? So I try to show you that there are some situations where probability, it's actually to me somewhat surprising that probability, it's hard to find examples where probability doesn't exist, because it seems that you're asking for quite a lot. You're asking for non-deterministic sequences to be convergent always to the same number somehow, right? So in that example as I gave down below, here it is, right? I'm saying that you see that you run the experiment once and you always see heads. You run it another time, you might see always tails. You see, so the ratio, if you're asking what's the probability of heads for this experiment, that probability does not exist. If you ask what's the probability that the machine will display always heads, that probability is 1/2. But the probability of heads does not exist, because strictly speaking, you run the simulation here, and one run it just produces heads, another run it will eventually produce just tails. So you have different experiments that produce different convergent values. So I try to create a very simple example of what it might mean to not have probability. You understand it? No. What bothers you then, Sarah?
Sorry, could you repeat what part doesn't have the probability of heads again. So you said one part does and one part doesn't.
Well,
So
what
could
I'm
you say that
saying
again?
is if this is the experiment, right? The experiment is, imagine, it's a bit weird what I'm saying. Imagine that you live in this simulation of this computer, right? So imagine you are a scientist living in this computer simulation. Okay. Now I turn you on, right? So when I press on,
I turned you on.
right, that's good. I hope I do.
Okay.
So
Okay.
I press on the button on, and now you are a scientist, and now you think, oh, I have this coin, right? I have this coin. Now let me throw it, and you think, oh my God, it always lands on heads. You understand? That's what I mean. So you look at this coin, you found this object, and you store it in the lab. Look at it. It's very magical, right? So I decide that my whim, I just press on, and then the scientist throws this coin, and it always comes up heads, always, without fail. I see that because of the setup that I'm on the outside of this universe. I can see that, why that would happen, right? Now, then imagine that when I turn off, the scientist has a memory of what happened before, the day before. Yes? Now I turn it on, and the scientist thinks, oh, it's gonna always be heads. It throws it around, and suddenly, oops, it's always tails. You see? On some days, it's always heads. On some days, it's always tails. Is very perplexed. Do you understand what I mean? That's what I mean by universe. I'm sorry for the earlier poor explanation. I was kind of not prepared today, but you understand my meaning. Yes, guys? So imagine you are performing this experiment, and what would you conclude? You conclude that this object is behaving very strangely. You might conclude that this object has no probability. A good book to read, by the way, is Solaris. Just mentioning, it's relating somewhat to such experiences, and there is also a great movie about it.
Can I just clarify?
Yes.
So it's not that sometimes it's always heads and sometimes it's always tails. It's always either always heads or always tails. When you
yes, but on the days when they perform the experiment. So one day he starts performing this experiment, and he always sees always heads. And then he wakes up the next day, even if he could perform in the day infinitely many experiments, it's always heads. Maybe the next day it would always be always heads, but there would be moments when he performs this experiment and it's always tails.
And so what you're saying is that the individual heads and tails has no probability, but the
yes, this coin that the scientist is holding, it has no probability.
Understood. Okay.
Right, but what the scientist can notice is this, right? You can notice that that the number of times he performs this the experiment producing always heads or always tails has a probability, right? Because he can notice if he just now looks at the actual experiments, how many of the experiments displayed heads, how many of them displayed tails, right?
So if you're looking at it experiment-wise.
Yes, the ratio of experiments producing heads to the total number of experiments has a probability of 1/2, but the coin itself does not have probability.
Okay. Okay.
Do you understand what I mean?
It's about perspective. Okay.
Well, I mean, maybe. I mean, it's a bit vague what's about perspective, but the coin itself, you see, the coin does not have probability, right? Understand what I mean? The coin itself does not have probability, but the experiments that display have it, at least in this example. Good? Interesting? Good. So probability is complicated, of course. You can see even already like this, right? What do you think about? Okay. So let's now continue talking about the axiomatic method. We will not go very deeply to it, but we will mention what it is. So you see, you can make probability very precise by omitting intuition. Okay. But the problem is that you can talk about something very precise and have no idea what you're talking about, or have very good idea of what you're talking about and not be able to prove it. It now becomes very difficult to prove. I do encourage you to think the way I presented before. I mean, all the formulas, you can establish them from that perspective, okay? From the belief that things have probability and that probability manifests itself once you run a sequence long enough. Okay, so here we have this situation. We have a sample space S, is the set of all possible outcomes. So for example, if you rolled a die, you might consider the set of possible outcomes to be 1 through 6. If you roll 2 coins, you might consider the set of possible outcomes. Those are the universes, right? So I'm presuming that my universe is very limited to 2 heads, head, tail, tail, head, tail, tail. We will later update it and see why is it reasonable to shrink universe so much, because I'm not throwing the coin in a vacuum. I might be throwing the 2 coins on a brown table in a dark room, or maybe the room is very well lit. It might be Tuesday or Wednesday. You understand? So why am I omitting all that information? That we talk about on the next in the next chapter. Good. Now, if you are trying to determine the lifetime of some flashlight, maybe the sample space could be from 0 to infinity minutes or hours, right? So S is just the collection of all possible universes that can come into existence as the result of the experiment being run. And little s in big S is just, it's supposed to be containing all the information about the particular universe that happens. Okay, so little s is the particular universe that comes to be. So we also call subsets of S events. Okay, it's so any subset for our purpose, every subset of S will be an event. So for example, if E is the event that the flashlight works longer than 5 hours, then E is the interval from 5 to infinity. But if we are talking about rolling a die, if E is the event that the number rolled is even, then E is 2, 4, 6. Good? Phi, what do you mean? Where is phi? I'm not sure I see any phi. Are you talking about some symbol? I'm sorry, I did not see any phi. Well, here we go. Ah, the empty set. Okay, I see. Thank you, Abhishek. Right, so the empty set is also naturally a subset. So you are all familiar with the power set, yes? The set of all subsets. So for our purposes, we will consider any subset of S to be an event. Okay, so I will also stipulate this. In my language, events may or may not have probability. You see, because if this set S is big enough, you can prove that there would always be subsets that do not have probability, right? But by that I mean, once you develop an axiomatic approach, you can very precisely explain what it means to not have probability, right? To not have measure. But for me, event is just any subset, just a synonym as to a subset. Good. So what do we have here? So we can, of course, take intersections, unions, and whatnot of 2 events within one subset. So for example, if we consider F to be the event that the number, the outcome from rolling a die is divisible by 3, then F is 3, 6. Good? And so we can say something like H is the intersection of the event E and F. That means just it's just 6. It means even and divisible by 3, there is only 6 as my outcome. If G is the union of even or divisible by 3, that's 2, 3, 4, 6. Okay. So empty set and S are also events in S. Good. We can take a complement naturally. Complement means just any outcome in the universe, in the set of universes S, that is not part of the event E, and that can be written as S minus E. Just throw away, take everything, but not outcomes in E. Good. And we have, of course, the following properties. We know that the union from k1 to n of ek, if you take the complement, it means, okay, the outcome is neither in a E1, nor in E2, nor in E3, and onwards. It's in none of them. That means it's in the intersection of not in E1, not in E2, not in E3. It's almost, it follows verbal logic almost, right? What does this mean, right? So it means not in E1 or E2 or E3, etc. So that means it's not in E1 and intersection is and. Not in E2, not in E3, and onwards. Clear? Anybody needs more explanation for one, or you understand it? Good. Now, similarly, two, the complement of the intersection is the union of the complements, right? So that means not in E1 and E2 and E3 and E4, right? So it must be either not in E1 or not in E2 or not in E3 or not, etc. So that's how you write it in set notation. Pretty clear why that works. Yes, guys? You can justify it by X in here, then X in, then that means if X belongs in this collection, then it belongs in that collection. And if X belongs in that collection, it belongs in that collection. But it's obvious verbally, I think. Good? So here are the axioms of probability. This is the way probability is defined. That's measure theory, basically. Okay, so probability is a function from the power set of S to R. And you understand what the power set means. It means any subset, any possible subcollection of S, it's a subset. So the probability is doing the following. This function will assign a number to any subset E. The number will be always between 0 and 1 for any E in S, right? The probability of S is 1. In other words, you're saying, of course, here you're trying to say, well, something in S will happen. At least one thing will certainly happen. So that's why you claim it to be 1, yes? Probability of S is 1 means that some outcome in S will actually be the result. And then next, if you have an infinite sequence of mutually disjoint, that's how we write, by the way, we will omit intersection and just write EI and EJ. If we have an infinite sequence where each two intersection is empty, then the probability of the union will be the sum of the probabilities. That will be an infinite series. So because of axiom 3, we use a lot of infinite series. Clear? Beautiful. So I want to make one remark, right? So I claim that the function P will work on any subset. Now, you don't have to worry about it in this class, but if S is uncountably infinite, that's impossible. You cannot construct a function satisfying axiom 1 through axiom 3 where it will always work. Okay, there will be some non-measurable subsets. Okay, so actually to define this probability over the total power set, if that power set is big enough, will be impossible. Good, but we will ignore that difficulty for this class. Now, here, guys, we are thinking entirely in a different way, right? Here we're thinking in terms of the axioms. Do you all understand roughly why somebody might have assumed axiom 1 through 3 as a good definition of what probability is doing, right? So here you're just saying that it's of course to infinity, but here you're saying that the probability of disjoint outcomes is the sum of those probabilities, right? And this means that we can assign a probability between 0 and 1. Again, we can think of initially there was this ratio, right? The number of successes divided by total number of trials should not exceed 1, because at the very best, I always have success when I have a trial, right? So the ratio should not exceed the number 1 and should not go below the number 0, because, well, if I fail all the time, then it will be 0 successes over whatever number of trials. Good? So with this, guys, can you please figure out, let's see if you can do that, what's the probability of the empty set? We will do it together in a moment, but just let's see if you can figure it out. And of course, I mean not by your intuition this time, but just by axiom. We no longer understand what probability is, but we try to figure out what is the, if we have axioms 1 through 3, what will be the probability of the empty set? Here are the axioms. Yeah. Too bad, James, you came a little bit late. You missed something that I think is interesting. I'm not sure if the others thought so, but.
Yeah, sorry about that. I was doing something, so.
No worries. It's nice you came anyhow. All right, guys, are we ready? Okay, so there are many things you can do. One thing you can try to do is use axiom number 3. Okay. You see, we are guaranteed the following. Look at it. We are guaranteed that if we take subsets of S that are disjoint, in other words, the intersection of any two of them is the empty set, then the infinite series of the union, of the probability of the union of them, right, will be, well, if I take probability of the union of such sets, it will be a convergent series. You can see it here, right? Probability of the union will be a convergent series. So that's what I intend to do here. Look at it. I can, let me just show you that this way. So I can set E1 equal to E2 equal to E3 forever and equal to the empty set. Yes? So I know that the empty set is equal to the union, well, n starts from 1 to infinity of En. Do you agree? Because empty set is the union of empty sets. And if I take nothing, I can write it as a union of many nothings. And of course, the intersection of any Ek with any Ej is the empty set. I omit the frown smile, right? I omit the intersection symbol here. The frown, I don't use it, right? I just write it like this. So that's empty set, right? So by axiom 3, what we have is the probability of the empty set is the probability of the union Good. And what is that? This, according to axiom 3, is the infinite series. You agree? I just add up En, all of them. But what is that? That's really the same as adding up the same number. So it has to converge. It's a number that is between 0 and 1 by axiom 3, and it has to converge. So that would be probability of the empty set, right? But the only way the series converges if the sequence, remember we mentioned that, if the sequence goes to 0. So we know that limit as n goes to infinity, the probability of En is 0. You agree? But it's always the same. It's never. It's a constant sequence. So that implies that probability of the empty set is 0. You understood how I reasoned? I use the divergence theorem. Okay, Sarah, what bothered you? You see, what do I know about the axiom? The axiom tells me this. If I take probability of disjoint, of countably many disjoint sets, all I have to do is add up the probabilities of each set. Yes? So what I can represent is that I can represent empty set as a union of many empty sets. A union of itself, right? I mean, intersection of empty set with itself is obviously empty set. Yes? So that follows trivially from axiom number 3. I just said I said empty set is equal to E1 union E2 union E3, where each of them is just the empty set. And so when what I do is that it's like adding up zeros. It's like I'm saying probability of the empty set is the probability of the empty set plus the probability of the empty set plus the probability of the empty set. This is what I'm claiming, you see? I'm claiming.
So are you claiming that because it's all empty set and that is equal to 0 because it reaches towards 0?
Yes. So I'm claiming that probability of the empty set is the probability of the empty set plus the probability of the empty set plus the probability of the empty set. Okay. In what sense? In the sense of partial sums. When we talk about series, right? So Jack, remember your trouble with sum of 2 and 2 squared and whatnot, right? So according to this sense, the limit is infinity, right? The limit is infinity if the series diverges. In the previous series that we considered, 2 plus 2 squared plus 2 cubed, but not, it will be infinity, because the only way that it can converge as a partial sum is if the terms that you're adding go to 0. So as I move on, those terms have to tend to 0. If this term is very far out, it has to tend to 0. But this term is actually always the same. So if it tends to 0, it must be 0. Because it doesn't change. You see, none of those, the sequence is constant. It doesn't change. Right? But as I look through the sum, I should see essentially addition of zeros. Right? It should look to me like I'm adding zeros. But if it looks to me like I'm adding zeros somewhere at the tail, that means that I'm adding zeros all the time. Clear? You will afterwards be allowed to forget this chapter. I mean, we'll not do it by axiom, because you see, it's kind of a lot of the formulas, you can see what they are and derive them and see if you are considering the running sequence. And you can link this idea to the limit of a running sequence and actually prove that the limit of a running sequence precisely converges to something through laws of large number. You know, the law of large number can do that. Okay, so there are theorems in probability that if you take it as an axiom, you can be sure that the running sequence converges. Okay, but here the meaning of probability is somewhat vague. What is the probability? What is it doing exactly? Okay. So I prefer the intuitive idea, which is very difficult to prove, but very easy to imagine what the situation is. Okay, and easy to derive many formulas, as I'll show you later.
Can you go back to when you use the divergence theorem for a second?
Huh?
Can you go back to where you wrote the divergence?
Okay,
theorem?
I think let me remind you of the divergence theorem. Sound
yeah,
good?
please do.
That's what I told you guys. You need to know series. So here is the divergence theorem, and let me try to explain to you why it's extremely intuitive. So I mean, the way it's written in the textbooks, whatever, right? You may forget, right? Think about it. Look at it, guys. Here is what we mean by, in Calc 2 or in calculus in general, what do we mean by infinite sum? What do we mean by that? This means nothing more than A1. This is first entry, A1 plus A2, second entry, right? A1 plus A2 plus A3, third entry, and so on. You see, you're seeing a sequence. And that sequence consists of other sequences, right? Now, you're supposed to see conversions. It's supposed to start to look like the same number, right? So eventually when you go down, it looks like the same number. So look at it, right? So imagine starting from substep n. This looks like some number s, right? But if that looks like the number s at step n plus 1, the actual thing that you will see is s plus a n plus 1, which also is supposed to look like s. You see, I'm kind of saying equal, but maybe I should say almost s, right? Maybe I'll do this so that it doesn't have to be s, but you stop distinguishing it from s. Yes, almost s. So how can this look almost like s? That's the only way that can happen if this thing looks almost like 0, right? So you understand what I conclude? It's very, very easy idea, guys. That the only way that a limit of partial sums can converge is if the terms of the added up sequence goes to 0. If the terms go to 0. Clear? Right? So that's what I do with this empty set proof. See? What I say is something like, well, P of the empty set equals to P of the empty set plus P of the empty set and onwards, right? That's by the axiom number 3. So what does it imply? That implies that the term of the sequence, those terms, right? As I look, I'm only seeing this term. I'm not seeing A1, A2, A3. I'm seeing the same term. As I look farther to the right, I'm supposed to begin to see additions by 0. But if I'm beginning to see additions by 0, it's a constancy. It doesn't change ever, right? It means that I'm actually seeing additions by 0, not something approaching 0, but actual zeros. You follow?
Yeah, okay, so it's converging to 0, basically.
So it converges. So the 0, I'm not sure what it converges to, but because that series converges, by hypothesis, it's supposed to P of empty set is between 0 and 1, because it converges, that forces the terms that I'm adding to equal to 0 precisely.
Okay, yeah. So
Good?
P of 0 is kind of like S in this example.
Yes. So
Okay.
P of the empty set is 0 because of that, by the divergence theorem, let's say. So you understand, guys, divergence theorem, nothing so special about it. It's extremely obvious what it is if you think about it intuitively. Good?
I got a quick question.
Go ahead.
So I don't know if this is the right analogy, but I kind of see it as like, I would say, if you ever play Sudoku, it's almost like I don't know if this is how I see it, right? So at every box, right, you're supposed to have like 9 numbers within that box, right? It cannot be the same number, right? But the possibility of having an empty box is still 0, if you understand what I'm trying to say.
Well,
It's like,
well, here's let me again, right? The funny thing about this chapters, you missed the moment when I talked about intuitive probability, right? If you want to, after class, I give you a quick debriefing. But if you want intuition, why is that 0? Imagine that you have an experiment where something is supposed to happen. Empty set means nothing happened, right? So when you press on, something is supposed to happen, right? So how many times will you see nothing happen? You will never see that. You understand? With the empty set, if the experiment tells you something must always happen, right? It's either outcome 1 or 2, or maybe you said in Sudoku, or I'm not sure in what. I don't play Sudoku. I don't know what it is. But I presume, let's say you said 9 objects in the box. So one of the 9 objects will be pulled out. Okay? Each time you play the game, one of the 9 objects is pulled out. Now, it's impossible, if that's the case, for nothing to be pulled out. Which means that if you count how many times nothing is pulled out over total number of trials, you will see 0 over first trial, 0 over second trial. So sequentially, you will, of course, see 0.
okay.
Doesn't a disjointed set represents a situation where nothing happens? Disjointed? No. Disjointed is this. Let me show you, Andre, what I mean by disjointed. So suppose we have the set E equals to 1 in the die, right? And E1 is equal to 1, E2 is equal to 2, right? So the E1 in E1 intersect E2 means that when I roll the die, both 1 and 2 happen. So the die displays the number 1 and the die displays the number 2. So the probability of the intersection is empty, right? is 0, because that's the empty set. It never is occurring. Good. And on the other hand, it maybe if probability of E1 union E2, that's just that's gonna be probability of E1 plus probability E2, because you have now two situations, either 1 or 2 happens. Okay, so you count it as a success when you get the number 1, and you count it as a success when you get the number 2. Good. But again, guys, so don't be too confused. We're kind of right now pretending we know nothing about probability and we have no assumptions, and we just have this axiom 1 through 3, and we're trying to derive the properties of the function. Okay, so we obviously know those results. We obviously think probability of the empty set is 0 without those calculations. But if we kind of want to make it rigorous, we lose all meaning of those terms and just play by the axioms and by those operations that are allowed. Clear? Now, here is the next question, guys. So I solved it differently, but I think that's longer than needs to be done. Now, here is the next problem, guys. Suppose we don't have infinitely many E1s, E2s, E3s, you know, right? They're disjoint, but they're only finitely many. Can you show that the probability of the union of E1 through En equals to the sum of the probabilities? Do you understand what I'm asking? No? Look at the axiom carefully. This axiom is telling you that if you have infinitely many mutually disjoint subsets of S, the probability of their union is the sum of the probabilities of each event individually. So I have to be doing that with infinitely many. Now, if I'm only given finitely many of them, only E1, E2, E3, all the way to En, how can I prove that even if it's finitely many, the probability of one plus the probability of the other will be the probability of the union? Okay, you understand what I'm saying? Let me just do it for 2. Probability of E1 union E2, where they are mutually disjoint. You see, I'm assuming E1 intersect E2, which, by the way, we will write E1, E2 is empty, right? Can you prove in that situation that it's the same as probability of E1 plus the probability of E2? By the way, guys, as the time is finished, I wonder if you want to hear that question or not. I found a pretty simple, let's see, for you it should be extremely simple question on what, when, where, because you're English speakers. It's actually, but the first part, it's actually a blitz consisting of 3 questions. The first question is simple. The second question, well, you will judge if it's simple or not. So if you want to hear it, stay and I'll show you that question. All right, guys, so our time came to an end. Think about it on your own, right? We will talk about this on Monday. And if you stay after class, if you want to discuss what we just spoke about, maybe it was not too hard. I mean, I'm assuming most of you understood what I had to say, but if you missed it or want to ask something about it, stay with me. All right, I'm gonna stop the recording and we will play